In this section, we'll continue to solve systems of linear equations, but this time we'll have 3 equations in each linear system. In the previous section, we saw that a linear equation on 2 variables represents a line inside R2. Let's go ahead and review this fact. Number 1, a linear equation on 2 variables is of the following form. Then, solving for y, we'll get the following equation. Then we clearly see that this is a line inside R2, whose slope is given by negative a2 divided by a1, and whose y-intercept is given by b divided by a1. Now, a linear equation on 3 variables represents a plane inside R3. We won't go into the details of how this is true. This is going to be reserved for Calc 3 and linear algebra. But let's go ahead and write out just the general equation of a linear equation of 3 variables. So this is going to be given in the following form. Again, this represents a plane inside R3, and the plane is actually going to be determined by this A1, A2, and A3. Let's go ahead and sketch a picture of an example of a plane inside R3. So R3 is a 3-dimensional analog of R2, where we have still an x-axis, a y-axis, but now we have a z-axis here. A plane inside R3 is just a 2-dimensional object that's flat. So here's an example of one plane living inside R3. Now, let's talk about linear systems. In the previous section, we had linear systems on 2 variables, and we saw that these linear systems represented how lines intersect. Let's again review this fact. Inside R2, we had 3 possible options. Either our lines intersected at one point, our lines intersected at every possible point, meaning they were the same line, or our lines never intersected, which means they were parallel. And I'm going to go ahead and label all the solutions of these intersections. Then, again, this represented that we had one unique solution for our linear system. This picture represented that we had an infinite number of solutions for our linear system, and this picture represents we had no solutions for our linear system. The surprising thing is that this is going to hold true for systems of linear equations on 3 variables. We'll either have one unique solution, an infinite number of solutions, or no solutions. Now, in this next scenario, we'll be looking at the intersection of 3 different planes. And we'll have one unique solution if all 3 planes intersect at one point. We'll have an infinite number of solutions if all 3 planes intersect at an infinite number of points or a line. And we'll have no solution if there's no common intersection between all 3 planes. So let's go ahead and sketch these pictures out. In picture number 1, we're going to go ahead and show how 3 planes can intersect at one point. I'm not going to draw the axis for R3, but again, remember that these planes are living inside 3-dimensional space. So here's our first plane here. Then here's our second plane. And finally, our third plane. And the thing that we notice is that the red plane and the blue plane intersect at one line, so namely this line here, and then the green plane and the blue plane intersect at this line here, and finally the green plane and the red plane intersect at this line here. So the only point in common is this point here. Now in case number 2, again, let's draw our red plane and our green plane the same way. So here's our green plane. Here's our red plane. and they intersect along this red line here. And if our blue plane also intersects this red line, then this is going to be the case where we have an infinite number of solutions to our linear system. So like this. So another way to picture this solution here would be, let's look at the two-dimensional analog. And if we look at this directly from the front, we'd see that we have a blue line, a green line, and a red line intersecting at this one point here. And behind these lines we have our planes going off in this direction. The final case is when we don't have any solution, and there's multiple different ways to draw how planes intersect. One possible case would be the following, and that's if we had three different parallel planes. Now let's go ahead and summarize everything that we just stated. A linear system of three equations has either zero solutions, one solution, or infinitely many solutions. And we're going to write this on the next page. Now, the solution set to equations of these types are going to be all ordered triples that make these equations true. Let's go ahead and compute an example where we try to decide if a given triple is a solution to a linear system. In this example, we're given the point 3, 3, negative 2, and we want to see if this solves this linear system here. And what we want to do is we want to plug this point into each equation. So let's go ahead and note that the first equation is going to be x minus y plus a 0 times z is equal to 0. The second equation is the same thing as x minus 0 times y minus z, which is equal to 5. And the third equation is x minus y plus z is equal to a negative 2. Plugging in 3 for our x values, plugging in 3 for our y values, and plugging in a negative 2 for our z, each equation is going to become the following. We'll get a 3 minus 3 plus 0 is equal to 0. Then we'll get a 3 minus 0 minus a negative 2 is equal to 5. Finally, we'll get 3 minus 3 minus 2 is equal to minus 2. And we see that the first equation is true, the second equation is true, and the third equation is true. So the point 3, 3, negative 2 is a solution. So a thing to note in this problem and all the remaining problems is that if you're given a linear system on 3 variables and you don't see a variable, then this is the same thing as multiplying a 0 times that variable and adding it or subtracting it.